Hello, space explorers. Welcome to Beyond Our Galaxy, where we explore the wonders of the universe. I'm Rushiel, and today we're diving into one of the most intriguing and mysterious phenomena in the cosmos: black holes. In this video, we'll uncover the complete life cycle of black holes, from their birth to their eventual death. So, let's embark on this cosmic journey together. A black hole is essentially a region in space where the gravitational pull is extremely intense. This happens when a massive star collapses under its own gravity at the end of its life cycle. The core becomes incredibly dense, forming what we call a singularity, surrounded by an event horizon, the point of no return. The concept of black holes was first predicted by the equations of general relativity, developed by Albert Einstein in 1915. However, it was Carl Schwarzschild who, in the same year, provided the first modern solution to Einstein's equations, which describes what we now call a black hole. The term black hole itself was coined much later, in 1967, by physicist John Wheeler. To understand black holes, we need to delve a bit into gravity. Isaac Newton described gravity as a force between two masses. However, Einstein's theory of general relativity revolutionized our understanding by describing gravity not as a force, but as the curvature of space-time caused by mass. Massive objects like stars and planets warp the space around them, and black holes are the extreme example of this phenomenon. There are different types of black holes, classified based on their mass and size. The three main categories are: 1. Stellar black holes. These form from the remnants of a massive star that has ended its life cycle and undergone a supernova explosion. Stellar black holes typically have a mass ranging from a few times that of our Sun up to about 20 times the Sun's mass. 2. Intermediate black holes. These are less understood and much rarer. They have masses ranging from hundreds to thousands of times that of the Sun. They might form through the merging of smaller black holes or other processes. 3. Supermassive black holes. These giants are found at the centers of most galaxies, including our own Milky Way. They have masses ranging from millions to billions of times that of the Sun. How they form and grow to such enormous sizes remains one of the biggest questions in astrophysics. 4. Primordial black holes. These hypothetical black holes could have formed immediately after the Big Bang due to high-density fluctuations in the early universe. They can have a wide range of masses, from very small to large, though their existence has not been confirmed. To grasp how stellar black holes form, let's briefly touch on the life cycle of massive stars. Stars are born from clouds of gas and dust, primarily hydrogen, in stellar nurseries. Through nuclear fusion, these stars convert hydrogen into helium, releasing immense amounts of energy and light. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core contracts, heats up, and may trigger a supernova explosion, leaving behind a neutron star or a black hole, depending on the mass of the original star. Stars with a mass less than about 8 times that of our Sun end their lives as white dwarfs, while those with masses between about 8 and 20 times the Sun's mass typically leave behind neutron stars. Only the most massive stars, those with masses greater than about 20 times the Sun's mass, have cores that collapse directly into black holes. At the heart of a black hole lies the singularity, a point where gravity is infinitely strong and space-time curves infinitely. Surrounding the singularity is the event horizon. The event horizon is the boundary beyond which nothing can escape. Anything that crosses this point is inevitably pulled towards the singularity. The region outside the event horizon is influenced by the black hole's immense gravitational pull, causing fascinating phenomena like gravitational lensing, where light bends around the black hole. Many black holes also have an accretion disk, which is a swirling disk of matter that is gradually being drawn into the black hole. As matter from the accretion disk spirals inwards, it heats up and emits X-rays and other forms of radiation, making these regions some of the brightest and most energetic in the universe. Black holes are born from some of the most dramatic and powerful events in the universe. To understand their birth, we need to look at the life cycle of massive stars. Stars are the cosmic powerhouses that light up our universe, and their life cycles are marked by stages of formation, stability, and eventually, a spectacular end. Stars are born in vast clouds of gas and dust, known as nebulae. Under the influence of gravity, regions within these nebulae begin to collapse, forming protostars. As the protostar's core temperature rises, nuclear fusion ignites, converting hydrogen into helium and releasing an enormous amount of energy. This marks the birth of a new star. Stars spend the majority of their lives in a stable phase known as the main sequence, where they steadily fuse hydrogen into helium. The length of this phase depends on the star's mass. Massive stars, those with at least 20 times the mass of our Sun, burn through their fuel much more quickly than smaller stars, leading to shorter but more eventful lifespans. As a massive star exhausts its hydrogen fuel, it begins to fuse heavier elements in its core, like helium, carbon, and oxygen. This process continues until the core is composed of iron. Unlike lighter elements, iron doesn't produce energy when it fuses. Instead, it absorbs energy, leading to a catastrophic situation. At this point, the star can no longer support itself against the force of gravity. The core collapses in a fraction of a second, resulting in a supernova explosion. This is one of the most energetic events in the universe, releasing more energy in a few seconds than our Sun will emit over its entire lifetime. During the supernova, the outer layers of the star are blasted into space, enriching the surrounding nebula with heavy elements. These elements are crucial for forming new stars, planets, and even life itself. Meanwhile, the core of the star continues to collapse under gravity's relentless pull. The fate of the collapsing core depends on its remaining mass. If the core's mass is between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star, a dense ball of neutrons. However, if the core's mass exceeds this limit, gravity overwhelms all other forces, and the core collapses into a black hole. This process gives birth to what we call a stellar black hole. Stellar black holes are typically found scattered throughout galaxies, each one a remnant of a massive star that once shone brightly in the cosmos. These black holes can have masses ranging from a few times that of our Sun to about 20 times its mass. The birth of a black hole is a reminder of the dynamic and ever-changing nature of the universe. From the violent death of a massive star comes the birth of one of the most mysterious objects in existence. These black holes, scattered throughout the cosmos, continue to captivate scientists and fuel our curiosity about the universe. Now that we know how black holes form, let's break down their structure and explore their fascinating anatomy. Despite being invisible, black holes have distinct parts that define their nature and behavior. At the heart of a black hole lies the singularity, a point where gravity is infinitely strong and space-time curves infinitely. The singularity is a region of infinite density where the laws of physics as we know them break down. It's a point where matter is crushed to an infinitely small point, and our current understanding of science can't describe what happens there. Surrounding the singularity is the event horizon. This is the boundary beyond which nothing can escape the black hole's gravitational pull, not even light. That's why black holes appear black. No light or information can escape once it crosses the event horizon. The event horizon is often referred to as the point of no return. Just outside the event horizon, there's a region called the photon sphere. Here, gravity is so strong that light can orbit the black hole. If you were to observe this area, you would see light bending in extreme ways, creating a distorted view of the universe behind the black hole. This effect, known as gravitational lensing, allows us to observe the surroundings of a black hole in unique ways. Many black holes also have an accretion disk, a swirling disk of gas, dust, and other matter that is gradually being pulled into the black hole. As matter from the accretion disk spirals inward, it heats up due to friction and gravitational forces, emitting X-rays and other forms of radiation. These emissions can make black holes some of the brightest objects in the universe, despite the fact that light cannot escape from within the event horizon. Some black holes, especially supermassive ones, can produce relativistic jets. These are powerful streams of particles that are ejected from the regions around the black hole at nearly the speed of light. These jets can extend for thousands of light years and are visible across vast distances. They play a significant role in the dynamics of galaxies, influencing star formation and the distribution of matter. Black holes have a profound impact on the fabric of space-time itself. According to Einstein's theory of general relativity, massive objects warp the space-time around them. In the case of black holes, this warping is extreme. If you were to venture close to a black hole, you would experience significant time dilation. Time would pass much more slowly for you compared to an observer far away. This means that a few minutes near a black hole could correspond to years or even centuries for someone at a safe distance. The intense gravitational forces near a black hole can also lead to a process known as spaghettification. If an object, or an unfortunate astronaut, were to get too close to a black hole, the difference in gravitational pull between the parts closer to and farther from the black hole would stretch and compress the object into a long, thin shape, like a piece of spaghetti. This extreme tidal force is why it's often said that black holes spaghettify anything that gets too close. Inside the event horizon, all paths lead to the singularity. Theories suggest that space and time switch roles in this region, making it impossible to avoid the singularity once crossed. However, this remains a topic of intense research and speculation, as our current theories of physics, including general relativity and quantum mechanics, do not yet provide a complete description of what happens inside a black hole. The anatomy of a black hole is as fascinating as it is complex. These cosmic enigmas challenge our understanding of the universe and push the boundaries of our knowledge. By studying black holes, we gain insights into the fundamental nature of gravity, space, and time, and open new frontiers in our quest to understand the cosmos. Over the past few decades, our understanding of black holes has significantly advanced, thanks to groundbreaking discoveries and observations. Let's delve into some of the most exciting recent findings that have reshaped our view of these mysterious cosmic objects. In April 2019, the Event Horizon Telescope 8 collaboration made history by capturing the first ever image of a black hole's event horizon. The image of the supermassive black hole at the center of the galaxy M87, known as M87*, revealed a bright ring of light surrounding a dark shadow. This shadow is the black hole's event horizon, and the image provided direct visual evidence of a black hole's existence, validating decades of theoretical predictions. Another monumental breakthrough came with the detection of gravitational waves. In 2015, the LIGO and Virgo observatories detected ripples in space-time caused by the merger of two black holes. These gravitational waves confirmed predictions made by Einstein's theory of general relativity a century ago. Since then, numerous gravitational wave events have been observed, revealing mergers between black holes and offering new insights into their properties and behavior. These detections have opened a new window into the universe, allowing us to study black holes in ways that were previously impossible. By analyzing the gravitational waves from these mergers, scientists can determine the masses and spins of the black holes involved and gain insights into the dynamics of these extreme events. NASA's Chandra X-ray Observatory has also made significant contributions to our understanding of black holes. By observing X-rays emitted by the hot gas in the vicinity of black holes, Chandra has provided detailed images and spectra that help scientists study the environments around black holes. For example, observations of the supermassive black hole at the center of our Milky Way galaxy, known as Sagittarius A*, have revealed flares and other phenomena that provide clues about the behavior of matter near the event horizon. Recent observations have also shed light on the powerful jets emitted by black holes. Studies using a combination of radio, optical, and X-ray telescopes have shown how these jets interact with their surroundings, influencing star formation and galaxy evolution. These observations help us understand the impact of black holes on their host galaxies and the broader cosmos. Another fascinating area of research is the study of tidal disruption events, where a star gets too close to a black hole and is torn apart by its gravitational forces. These events provide a unique opportunity to study black holes as they consume stellar material. Recent observations have captured these dramatic encounters, offering valuable data on the feeding habits of black holes and the extreme physics at play. Advances in computer simulations have also played a crucial role in our understanding of black holes. High-resolution simulations allow scientists to model the complex interactions between black holes and their environments, providing detailed predictions that can be compared with observations. These simulations help us visualize the behavior of black holes and explore scenarios that are challenging to observe directly. The future of black hole research looks incredibly promising, with new telescopes and missions on the horizon. The James Webb Space Telescope, set to launch soon, will offer unprecedented infrared observations that could reveal new details about black holes and their surroundings. Other upcoming missions, such as the Laser Interferometer Space Antenna LISA, aim to detect gravitational waves from space, providing even more data on black holes and their mergers. These recent discoveries and observations highlight the rapid progress we've made in understanding black holes. Each new finding not only confirms our theories, but also raises new questions, driving further research and exploration. By continuing to study black holes, we deepen our knowledge of the universe and uncover the mysteries of these fascinating cosmic objects. One of the most profound aspects of black holes is their impact on space-time itself. According to Einstein's theory of general relativity, massive objects cause a distortion in the fabric of space-time. Black holes, with their immense mass concentrated into an incredibly small area, create the most extreme warping of space-time known in the universe. To visualize this, imagine space-time as a two-dimensional rubber sheet. When you place a heavy object, like a bowling ball, on this sheet, it creates a depression. Smaller objects placed on the sheet will roll towards the heavy object due to this depression. Similarly, black holes create a deep well in the fabric of space-time, causing anything nearby to be pulled towards them. One of the most intriguing consequences of this extreme warping is time dilation. Near a black hole, the gravitational pull is so strong that it significantly slows down time. If you were to observe an astronaut near a black hole, their movements would appear to slow down dramatically compared to someone far away from the black hole. This means that time near a black hole moves much slower than it does elsewhere in the universe. This concept, though mind-bending, has been confirmed through various experiments and observations. The closer you get to the event horizon, the more pronounced these effects become. At the event horizon itself, time appears to stop altogether from the perspective of an outside observer. This effect is not just theoretical. It's a fundamental prediction of general relativity. supported by observational evidence from systems where black holes interact with other astronomical objects. Another remarkable effect of black holes on space-time is gravitational lensing. Because black holes warp the space-time around them, they can bend the path of light passing nearby. This bending causes distant stars and galaxies to appear distorted or magnified when viewed from Earth. Gravitational lensing not only provides a method to detect black holes, but also acts as a cosmic magnifying glass, allowing us to study objects that would otherwise be too faint or distant to observe. The intense warping of space-time by black holes also leads to fascinating theoretical concepts, such as wormholes. A wormhole is a hypothetical tunnel-like structure that could connect distant points in space-time. While no observational evidence for wormholes exists yet, they remain a popular subject of scientific investigation and science fiction, inspiring thoughts about potential shortcuts through space and time. If an object or person were to venture close to a black hole, they would experience spaghettification due to the immense tidal forces. This process involves the object being stretched and compressed into long, thin shapes. The closer to the black hole, the more intense these tidal forces become, eventually tearing apart anything that crosses the event horizon. At the center of a black hole lies the singularity, where space-time curvature becomes infinite and the laws of physics as we currently understand them break down. This region poses one of the greatest challenges in modern physics, as we lack a complete theory of quantum gravity to describe what happens in these extreme conditions. The singularity remains a mystery, inviting further research and exploration. Black holes and their interaction with space-time push the boundaries of our understanding of the universe. They challenge our concepts of space, time, and gravity, providing a natural laboratory for testing the limits of physics. As we continue to study these enigmatic objects, we not only gain insights into their nature, but also learn more about the fundamental workings of the cosmos. By exploring black holes and their effects on space-time, we are delving into the very fabric of the universe. These studies help us understand the profound connections between gravity, space, and time, and reveal the extraordinary nature of the universe we inhabit. Just like stars, black holes have life cycles, and yes, they can die. The concept of the death of a black hole might seem counterintuitive, but it's a fascinating process governed by the laws of quantum mechanics and general relativity. Let's explore how black holes, the most massive and seemingly eternal objects in the universe, can eventually fade away. The key to understanding the death of a black hole lies in a process called Hawking radiation, proposed by the theoretical physicist Stephen Hawking in 1974. According to this theory, black holes are not completely black. Instead, they emit a very faint radiation due to quantum effects near the event horizon. Hawking radiation arises from the strange properties of quantum mechanics. In the vacuum of space, particle-antiparticle pairs are constantly popping into existence and then annihilating each other. However, near the event horizon of a black hole, one of these particles can fall into the black hole, while the other escapes into space. The particle that escapes carries away a tiny amount of the black hole's mass and energy, causing the black hole to lose mass over time. This process is incredibly slow. For a black hole with the mass of our Sun, it would take far longer than the current age of the universe for it to evaporate completely. As the black hole loses mass, it shrinks and its temperature increases, causing it to emit more Hawking radiation and accelerate the evaporation process. As the black hole continues to lose mass, this evaporation process accelerates. Eventually, the black hole reaches a critical point where it radiates away its remaining mass in a final burst of energy. This dramatic end is sometimes referred to as a black hole explosion, although it's important to note that it's not an explosion in the traditional sense, but rather a rapid release of the last vestiges of the black hole's energy. smaller black holes, such as those potentially formed in the early universe or through high-energy processes, would evaporate much faster. These hypothetical micro-black holes would have shorter lifespans and might evaporate completely within a human timescale. But no such black holes have been observed yet. The death of a black hole has profound implications for our understanding of physics. It suggests that black holes do not last forever, and that they can transform the way we think about the conservation of information in the universe. One of the most intriguing puzzles arising from Hawking radiation is the black hole information paradox. According to quantum mechanics, information about the physical state of matter must be preserved. However, if black holes eventually evaporate completely, what happens to the information about all the matter that fell into them? Various theories have been proposed to resolve this paradox. Some suggest that the information is somehow encoded in the Hawking radiation, while others propose that the information could be preserved in a remnant or stored on the event horizon itself. This ongoing debate is a key focus of research in theoretical physics and has led to new insights into the nature of black holes and quantum gravity. In the future, advanced telescopes and detectors might allow us to observe the effects of Hawking radiation directly or indirectly, providing further evidence for this fascinating process. Such observations would not only confirm Hawking's groundbreaking theory, but also deepen our understanding of the life cycle of black holes and the fundamental laws governing our universe. Visuals: compilation of black hole life cycle, from birth to death. Your name. From their formation to their eventual evaporation, black holes offer a unique window into the extremes of the universe. Studying their birth, anatomy, and death helps us explore the boundaries of physics and enhances our comprehension of the cosmos. By understanding the death of black holes, we continue our journey to unravel the mysteries of the universe, pushing the frontiers of human knowledge. Black holes are among the most fascinating and enigmatic objects in the universe. From their mysterious birth in the hearts of massive stars to their eventual evaporation through Hawking radiation, they challenge our understanding of physics and inspire awe. By exploring black holes, we gain insights into the very fabric of space-time and the fundamental laws that govern our universe. As we continue to study black holes, we stand on the brink of new discoveries that could revolutionize our understanding of the cosmos. Future missions and advanced observatories will provide even more detailed observations, helping us to answer some of the most profound questions about black holes and the universe itself. Here at Beyond Our Galaxy, our mission is not only to explore these incredible phenomena, but also to provide a serene and relaxing experience for our viewers. We believe that the wonders of space can also be a source of peace and tranquility, helping you to unwind and sleep better. If you've enjoyed this journey through the life cycle of black holes, don't forget to like this video and subscribe to our channel. By subscribing, you'll stay updated with our latest videos on space exploration, cosmic phenomena, and more. We have an exciting lineup of playlists covering topics like exoplanets, the mysteries of dark matter, and stunning cosmic landscapes, all designed to both educate and relax you. Be sure to check out our playlists, such as Galactic Journeys, where we explore the wonders of our universe, and Cosmic Relaxation, a collection of soothing space visuals and ambient music perfect for winding down. Each playlist is carefully curated to provide both informative and calming content. We'd love to hear from you. Let us know in the comments what topics you'd like us to cover next, or share your thoughts on today's video. Your feedback helps us create the best content possible. Follow us on social media to stay connected and join our community of space enthusiasts. You'll find behind-the-scenes content, updates on upcoming videos, and more opportunities to engage with us. Thank you for watching Beyond Our Galaxy. We hope you found this exploration of black holes both fascinating and relaxing. Until next time, keep looking up at the stars and dreaming of the cosmos. Remember, the universe is vast, and there is always more to discover. Join us on this incredible journey as we venture beyond our galaxy. Stay curious and keep looking up.